Imagine a world without electricity, a world where the only sources of light are candles and the sun, where the night is truly dark and silent. No lights to guide you, no phones to connect you, no computers to work or play on. The conveniences we take for granted would be non-existent. It's hard to picture, isn't it? The absence of electricity would fundamentally change our way of life, leaving us in a state of confusion and disbelief. Our modern world is built on electricity. From the bright lights of city skylines to the buzzing offices filled with computers and phones, electricity is the lifeblood of our civilization. But where does it come from? How is this essential force generated and harnessed to power our daily lives? How do we generate this invisible force that powers our lives? The answer lies in the intricate dance between electricity and magnetism. The answer lies in a fascinating phenomenon known as electromagnetic induction. This principle was discovered by the brilliant scientist Michael Faraday in the early 19th century. This fundamental principle of physics describes how electricity and magnetism are intimately linked. It explains how a changing magnetic field can create an electric current. It's the magic behind many of the technologies we rely on every day. From the smartphones in our pockets to the electric cars on our roads, electromagnetic induction is at work. In essence, electromagnetic induction is the process of creating an electric current in a conductor by changing the magnetic field around it. This can be achieved by moving a magnet near a coil of wire or by changing the magnetic field within a stationary coil. This means that moving magnets or changing magnetic fields can induce electricity to flow. It's a simple yet powerful concept that has revolutionized the way we generate and use electricity. It's a remarkable concept with profound implications. The ability to generate electricity through electromagnetic induction has opened up endless possibilities for innovation and technological advancement. The discovery of electromagnetic induction revolutionized our understanding of the universe and paved the way for countless technological advancements. From Faraday's early experiments to the modern power grid, this principle has been at the heart of our progress. Join me as we delve deeper into this captivating phenomenon, exploring its history, principles, and real-world applications. Together, we'll uncover the secrets of electromagnetic induction and see how it continues to shape our world today. To grasp the essence of electromagnetic induction, we must first understand the invisible forces at play: electric and magnetic fields. These fields are fundamental to the workings of our universe, influencing everything from the smallest particles to the largest cosmic structures. These fields surround charged particles and magnets, respectively, influencing the space around them. Charged particles create electric fields, while magnets generate magnetic fields, each exerting forces that can affect other objects within their reach. Think of a magnetic field as invisible lines of force emanating from a magnet. These lines extend from the North Pole to the South Pole of the magnet, creating a loop that returns to the starting point. These lines, often visualized using iron filings, represent the direction and strength of the magnetic force. The denser the lines, the stronger the magnetic field in that region. Similarly, an electric field surrounds any object with an electric charge. This field exerts a force on other charged objects, either attracting or repelling them, depending on the nature of the charges involved. Now imagine moving a magnet near a wire. This simple action sets the stage for a fascinating phenomenon. The changing magnetic field interacts with the electrons in the wire, causing them to move. This movement is not random but follows a specific direction dictated by the magnetic field. This movement of electrons is what we call an electric current. It's the flow of these tiny charged particles that powers our electronic devices and lights up our homes. The faster the magnet moves, or the stronger the magnetic field, the greater the induced current. This principle is harnessed in generators and transformers to produce and manage electrical power. This direct relationship between the changing magnetic field and the induced current is at the heart of electromagnetic induction. It's a principle that has revolutionized technology and industry. It's a delicate dance between two fundamental forces of nature. This interplay not only explains how we generate electricity, but also reveals the interconnectedness of the physical world. In the 19th century, a brilliant scientist named Michael Faraday conducted groundbreaking experiments that unveiled the secrets of electromagnetic induction. His observations led to the formulation of Faraday's law of induction, a fundamental principle that quantifies this phenomenon. Faraday's law states that the magnitude of the induced electromotive force, or voltage, is proportional to the rate of change of the magnetic flux through a circuit. In simpler terms, The faster the magnetic field changes, the stronger the induced current. This law provides a mathematical framework for understanding and predicting the behavior of electromagnetic induction. It allows us to calculate the amount of current induced in a conductor based on the changing magnetic field. Faraday's contributions revolutionized our understanding of electricity and magnetism. While Faraday's experiments laid the groundwork for understanding electromagnetic induction, it was James Clerk Maxwell who took these concepts a step further. Maxwell, a Scottish physicist, developed a set of equations that elegantly unified electricity and magnetism into a single elegant theory, electromagnetism. Maxwell's equations, a cornerstone of classical physics, describe how electric and magnetic fields are interrelated and how they propagate through space as electromagnetic waves. These waves, which travel at the speed of light, encompass a vast spectrum of radiation, including visible light, radio waves, and X-rays. Maxwell's work not only provided a theoretical framework for electromagnetic induction but also predicted the existence of electromagnetic waves. This prediction was later confirmed by Heinrich Hertz, who experimentally generated and detected radio waves, paving the way for the development of modern wireless communication. Section 5. The transformer, taming electricity for everyday use. One of the most significant applications of electromagnetic induction is the transformer. This device has revolutionized the way we manage and utilize electrical energy. This ingenious device, found in countless electronic devices and power grids worldwide, allows us to control the voltage of alternating current, or AC, electricity. By adjusting the voltage, transformers make it possible to efficiently transmit electricity over long distances and safely use it in our homes and businesses. A transformer consists of two coils of wire wrapped around a shared iron core. These coils are known as the primary and secondary coils. When AC current flows through the primary coil, it creates a changing magnetic field that induces a current in the secondary coil. This process is known as electromagnetic induction. The number of turns of wire on each coil determines the voltage transformation ratio. For instance, if the secondary coil has more turns than the primary coil, the voltage is stepped up. Conversely, if the secondary coil has fewer turns, the voltage is stepped down. Transformers can either step up the voltage for long-distance transmission, or step it down for safe use in homes and appliances. This versatility makes them indispensable in our electrical infrastructure. Without transformers, our modern electrical grid would be impossible. They enable the efficient transmission of electricity from power plants to urban and rural areas alike. They are essential components in power distribution systems, ensuring that electricity reaches our homes and businesses at the correct voltage. This not only enhances safety, but also improves the reliability and efficiency of our electrical supply, making modern life as we know it possible. Section 6. Generators from mechanical energy to electric power. Another crucial application of electromagnetic induction is the electric generator. This device, found in power plants worldwide, converts mechanical energy into electrical energy, providing the foundation for our modern electrical grid. Generators operate based on the principle of electromagnetic induction. A rotating coil of wire, called an armature, is placed within a magnetic field. As the armature rotates, the magnetic flux through the coil changes, inducing an electric current. The mechanical energy to rotate the armature can come from various sources, such as steam turbines, wind turbines, or hydroelectric dams. Generators are essential components of power plants, providing the electricity that powers our homes, businesses, and industries. Section 7. Induction cooking, heating without flames. Beyond power generation and distribution, electromagnetic induction also finds applications in our kitchens. Induction cooktops, increasingly popular in modern homes, use this principle to heat cookware directly, offering precise temperature control and energy efficiency. An induction cooktop contains a coil of wire beneath its smooth surface. When an alternating current flows through the coil, it generates a rapidly changing magnetic field. This field induces eddy currents in the ferromagnetic base of compatible cookware, causing it to heat up. Unlike traditional gas or electric stoves that heat the air around the cookware, induction cooktops directly heat the pot or pan, resulting in faster heating times and reduced energy loss. Induction cooking offers a safer, more efficient, and more responsive cooking experience. Section 8. Wireless charging, cutting the cords. As technology advances, we strive for greater convenience and freedom from wires. Wireless charging enabled by electromagnetic induction is rapidly gaining popularity, allowing us to charge our smartphones, smartwatches, and other devices without the hassle of cables. Wireless chargers utilize a transmitter coil that generates a changing magnetic field. When a compatible device is placed on the charging pad, the receiver coil within the device interacts with the magnetic field, inducing a current that charges the battery. This technology eliminates the need for physical connectors, offering a more seamless and convenient charging experience. As wireless charging technology continues to evolve, we can expect to see its integration into a wider range of devices, further reducing our reliance on cords.